Hello everybody, welcome to section 2.5 in our college algebra and trig book. The next topic has to deal with properties of graphs. In this particular section, we'll be talking about the idea of symmetry, even and odd functions, translations and reflections and compressions and stretchings of graph. How does all of that accomplish? So our first task is to address this idea of symmetry. Symmetry is a really simple idea. It was taken to mean how graphs look the same on either side of some line. And in this case, we consider symmetry about the x-axis, y-axis, and even about a point, the origin. And we look at how do we determine these symmetries. This graph right up here that you see in the top corner, and I'll just pick it up and drag it down with us here. This particular graph has what is called symmetry about the y-axis. It looks as though you could hold a mirror to the y-axis and see the same picture on either side. So if we have symmetry about the y-axis, what sort of properties could we determine? Well, for one thing, if we have an x and y coordinate point on one side, there will be a certain similar x and y coordinate on the other side. More specifically, for some value of x, we'll get the same value of y to give us this coordinate xy as if we put in the negative of that value of x and got the same value of y. So this would be symmetry about the y-axis. In other words, when we have graphs that show this property, we say there's symmetry about the y-axis. The next graph over here in green, if I can get this thing to snag it, there we go, okay. The next graph over here is said to have symmetry about the x-axis. The thing about symmetry about the x-axis is that it's similar to symmetry about the y-axis, except that for any given value of x, this time we get two values of y. So x could give us positive y as a value, or x could give us negative y as a value. When this is the case, this is very similar to that symmetry about the y-axis. We will say, however, that a graph that has symmetry about the x-axis is not a function. Y is not a function of x because it doesn't pass the vertical line test. And then finally, we can talk about symmetry about the origin. Symmetry about the origin is a little different than these two in that the symmetry of the graph is no longer about a line, but about a point. In this case, the point is the coordinate 0, 0. And what we say about this is that if there is symmetry about the origin, if we take a point x and find the y value that corresponds to it, to get our coordinate here on this side of the graph, if it is symmetric about the origin, then going to the negative of that value of x results in a y value that is the negative of the y value on the other side. So in other words, if it passes through x and y, it would pass to the point negative x, negative y on the other side. So these symmetry properties we can use to help us determine symmetry of a graph of a function without even having to draw the graph. So that's the question. How do we do that? Well, in this particular case, let's check it out. If if an equation representing a graph that is symmetric to the y-axis, we can test it by replacing x with negative x and see what happens. In this case, is it symmetric about the x-axis? Well, if we rewrote this equation by replacing x with negative x, it changes the nature of the equation. In other words, the same values of x and y that satisfied the guy up here would not satisfy this one up here. So our answer would be no to the y-axis. How about the next function? Absolute value of x plus y equals 4. If we replace x with negative x, does it change the kind of values that we would get for this function? Well, in this particular case, no, it does not, because absolute value of negative x is equal to absolute value of x. So in this particular case, we would say, yes, it is symmetric to the y-axis. How about our last one? What if we replace x with negative x here? Well, we're going to see the same deal as we did in the first graph, raising negative x to the third minus y. We change the values of x that go into this function. We change this function because negative x cubed is the same thing as the negative of x cubed. So no, this is not symmetric to the y-axis. That's our first test. Our next test is how do we test to see if it's symmetric to the x-axis? Well, if the equation represents a graph that's symmetric to the x-axis, replace y with negative y and see what happens. How about this first one? Well, replacing y with the negative of y gives us the same set of values as a solution set in this particular equation. Negative y squared, the negative of y squared, is exactly equal to y squared, and so we would say yes, this graph is symmetric to the x-axis. Whatever it looks like. We don't actually have to know, we just need to know what this test tells us. How about in our next case? Well, in this case, no, because the absolute value of x plus negative y does change the nature of the equation, so that we would be taking the absolute value of x minus y equals 4, and that's a different equation. So we would say no, this one is not symmetric to the x-axis. How about our last graph? Well, in this case, kind of like the first, x cubed minus negative y is equal to 0, which becomes x cubed plus y when rewritten equals 0, and we come to the conclusion that this guy is not the same, and therefore it is not symmetric to the x-axis. Okay, how about equations that represent graphs symmetric to the origin? We're going to replace both. When I say both, I mean both x with negative x and y with negative y. So if we check our first equation by doing that, we're going to get the negative of x plus the negative of y squared is equal to 4. And simplifying that equation gives us negative x plus y squared equals 4. And that is just like the first case that we had. So we're going to say not to the origin. How about the second case? Well, if we test this one by replacing x with negative x and y with negative y, we wind up with the same situation that we had when we were testing x-axis symmetry. The absolute value of negative x is the same thing as the absolute value of x, but we'll be subtracting y to get 4, and since that changes the nature of this equation, we were going to say that this one's not symmetric to the origin. How about our last graph? Well, if it's symmetric to the origin, we replace x with negative x replace y with negative y, and see what happens when we rewrite it. Well, we're going to get the negative of x cubed plus y is equal to 0. And you might think to yourself, well, that's not the same as the original equation, except that we can divide both sides of this equation equally by negative 1. And lo and behold, we get the original equation out. When that's the case, we say that there is symmetry to the origin. So this graph does have symmetry to the origin. Okay, so more talk about symmetry in graphs in the next video.